Alright, let's try this again. We are doing an exam with mathematical physics tomorrow. So let's focus on the Fourier transform. And as we can see, if we're going into the Fourier transform, like we have a regular function and we want to figure out what the Fourier is, then we can see that we're looking for e to the positive ikx, or e to the positive iwt. And if we want to return to the original function, we would need to use a negative, e to the negative ikx. So, here's an example where we're taking sort of the function 1. We're taking the integral over e to the ikx, and then we're going to get 2 pi with this delta function. Or we can take the reverse, and we can go delta function back to 1. And so basically, this is kind of the basics of the Fourier transform, which I'm sure we have used plenty of times before. But it's going to come in handy in this particular exam. So let's head over to the Green's function, which I think is going to be a little bit more important. So now, the idea is we have like a pebble, and it's going to be going into a pond of water. And when that happens, let's say it's in the center, this particular pebble is going to make large ripples in this water. This particular pebble is on the side. The ripples are going to be a little smaller. So the idea is the Green's function is going to encode how these pebbles will create disturbances, or how the system is really going to respond to these pebbles. So the Green's function just tells you how sensitive this pool is at each particular point when we toss in a pebble, and the kind of ripples that will appear from it, or the particular frequencies. So that's a really cool way to think about this. Now, let's see, where do we want to start? I think we start down here. So the idea is that we have this definition of the Green's function, where we're taking some kind of derivative of the Green's function, and that gives us a delta function at that point. Okay, and here's an example. We take the d over dx plus some constant k, and we multiply it by f of x. We'll call that the Green's function, and we get a source, s. We can try to take these integrals, like look, the derivative of the response is the source. That reminds you that this is actually the Green's function is the f of x, I guess. I don't know, this is a little bit complicated, but the idea is, here you go, we could use, in order to get the source, you can integrate the source point over all the sources. But I think it's a little better to find the solution, because the solution, when you try to find the response, you take the integral of the Green's function times the source function, and you want to do it over this d prime target rather than the regular old x target. So you can get your solution like that. Now it's important to go into Fourier space with this concept. And, well, when we go into Fourier space, let's look at how this kind of works. You essentially have to replace any kind of derivative, like d over dx or something. We're going to replace that with an ik. Alright, so if we see this thing where we have d over dx, we're replacing it with our ik. And since we have a dx squared here, for example, then we would do an ik squared. And when we do that, we get a negative k squared here. So this should be negative alpha k squared, which we already saw before. We can Fourier from delta back to 1. So this is kind of how we can take a very simple Green's function Fourier. Now, why do we get these little dx equals negative iw, or these particular results for these differentials? Is because we can assume a regular plane wave like this, e to the I kx minus wt, And the reason why we have it in the positive k direction and the negative time direction is just because that's how we get a right moving sign on both sides, and you're left with dt equals negative iw. Same thing with this dx squared. We take a double derivative of this function here, and we get ik. You could square that if you want to. You get a negative k squared. So yeah, cool. This is actually really fun stuff to do, and you get a couple different types of Green's function. Here's another one where we, instead of having like a time differential plus a alpha times a double space differential, we just have a space differential with a constant. And here, for example, is exactly what we're talking about. We have d over dx times the gx, and it Fouriers, and it just becomes negative ik times the g squiggle. Awesome. An important part about the Green's function is that it obeys causality. It encodes causality in the function, really. Where if you have t is less than 0 at negative times, you don't get any response, which makes sense because that's in the past. So you can't get a response from the past. You can only get a response from positive time in the future. So, I don't know. They're trying to encode causality like this by basically using this step function, or the heaviside step function, where at t is less than 0, this particular angled function, the heaviside function, theta, is equal to 0. And at positive times, you're equal to 1. So many Green's functions are proportional to this. So I guess I have to kind of write it, I don't know, I'll write it here. So usually Green's functions, maybe if x, t, are going to be proportional to the heaviside function. Often with some sort of a exponential or something after it. But this rule is pretty important. I guess we have to kind of put it around here. Encodes causality. Yeah, it's a little bit sloppy, but so your Green's function is often going to be proportional to the heaviside step function. And when we do that, the types of integrals here, we kind of have to consider whether our t prime, like comparing the t and the t prime, because the t will tell us kind of where we are on the slider, I guess. The t goes from, regular t goes to 0 to infinity, and the t prime will go to something more finite, like 0 to pi or 0 to capital T. The reason is, if we were to integrate something all the way to infinity, then it becomes infinite, and that's not good. So we usually have this t prime variable, which we're always integrating over the prime variable, as you can see. And when we do that, we should stop at a finite number. And then we can compare whether t is less than this, I'll call it capital T. So this is our capital T. It's our finite time that we're going to integrate up to. And we ask ourselves, where is the t in the meantime? Is t going to be less than the max value of t? If that's the case, then when you take the minimum of t and the maximum, what do you get? What's less? A t that's sort of varying between 0 and capital T, or the capital T? And the answer is right there. It says that it's actually t. T is less, it's the minimum value between the ranging t and the capital T. And that's because we're always less than capital T in this particular example. So obviously the lowercase t is going to be the lower number. So there we go, we take the min of t, and when we take the min of t, that becomes our integration limits, usually for the response or maybe for the Green's function integral. But yeah, so we're basically going from 0 to lowercase t. But if we have t is greater than the maximum value of t, then ask yourself, what is the lower value? What's the minimum? Is it capital T or lowercase t in that case? And the answer is capital T. That looks pretty good. And here we'll put the capital T. So because t is greater than capital T, then obviously t is the lower bound. And so now we take the integral, we stop at the lower bound t. So we're kind of always grouping our results into 3 different types of segments. Segment 1 is going to be time is less than 0. Segment 2 is when time is less than t. And segment 2 is when time is greater than this t. So those are the 3 segments we can use. Okay. In fact, there's going to be 3 integrals. Let's extend this a little bit more down here, because the third integral is the first integral, which is supposed to be time is less than 0, and usually this is usually 0. Just like the integral value is usually just equal to 0. So that's fine. And so we're more interested in the second 2 integrals that happen at later times. Awesome. So this is pretty cool. The Green's function and its responses are quite interesting. But let's head on to the next concept, which I guess is convolution. I mean, we have this. We can do convolutions of this Green's function like this. We take the response and multiply that by Green's function times the source, and you kind of get your response Fourier. It's kind of interesting. Whatever, let's skip over that, and let's go into the branch cuts. So this is the next part. Branch parts are like a completely different topic now, so we're just like jumping into a new concept. So the branch cuts are interesting. So they will happen for functions that are fractional powers, like square roots. They'll happen with logarithms, log z minus a, and they'll happen with inverse trig functions like, arc cosine, arc sine, arc tan. So let's focus on the square root functions. The idea is that the branch points is kind of where the function becomes equal to 0. So you just say z minus a. If you plug in an a, then this function becomes 0. Or rather, the inside of the function, the argument becomes 0. And so a becomes the branch point. Now what does that mean? Let's say we just had square root of z, meaning that your branch point was just a equals 0. So z naught is equal to 0. Then you have to take this little Taylor series expansion, where you start, so in z naught plus epsilon, which is this tiny, tiny, tiny radius around that point, epsilon. And you have e to the I theta over 2. And you do that, do a little Taylor series expansion, and then, you kind of ask yourself, all right, what would be if we added plus 2 theta, or 2 pi to the theta, and we go around a circle? What's the solution? What's the answer? We return to the regular old e to the I theta over 2, but then we have this e to the I pi that's sitting out here, that's multiplied by this, and that causes a sign flip to the original e to the I theta over 2. So because of that, we sort of learn that there's a branch point. Now this is sort of the very rigorous way to define a branch point. But it's just a little bit easier to think of it in terms of like, all right, if you have a square root function and you plug in, like, what's going to make the argument of the square root function? Whatever's inside of it. This stuff right here inside z minus a, that's the argument of the square root function. And what's going to make that 0 is just a equals 0. And if we have the square root of z, what's the branch point? It's just 0. And what does it look like? It looks like a point right there at the origin, and then we're going to swirl around it with a little loop like that with a radius of epsilon. Really, really, really small radius. So the idea is that, like, you can keep adding these 2 pi n angles to the theta. And you keep spinning around, spinning around, spinning around the circle. But it would be nicer if we could just kind of block off maybe negative pi to pi as our branch cut, so to say, and restrict the angle between them. So we only have one solution, negative 1 equals e to the I pi, for example. And that's the only way that we can represent negative 1. You should be able to represent it with theta plus 2 pi n, but we're going to stop and we're going to cut out all the extra n's, and we're just going to focus on the one that's pi, for example. So that's good for like square root functions. If we're doing a logarithm, here's another example. So ln of z, and the complex log, like if you take a log z, it's really equal to this. The ln of the magnitude of z plus I arg z. What's arg z but just this? Theta plus 2 pi n. So we take the ln plus I, theta plus 2 I n, and this would be something that doesn't have a branch cut. We're just letting it spin around and around and around forever. But if we wanted to have a branch cut, then we could take a couple standard cuts, like negative pi to pi is a cut. That cut looks like negative infinity to 0. Why? Well, because you have your unit circle like this, and you cut it from negative infinity to 0, then it forces you to be restricted within, from here all the way around the loop, negative pi to pi. And you kind of stop right here, and you start right here. So you're kind of restricted to this particular portion of the circle. I guess I could put that like here. So this is the negative infinity to 0 branch cut, and it stops right here at the origin, like that. Boom, that's your branch cut. And then here's your little integral as you go around the circle. Awesome. But you could also have a cut that goes from the other way, like 0 to 2 pi. And if we did that, a 0 to 2 pi branch cut would look a little bit more like this. And then we could draw a circle like that. And what does this give us? Well, we get a 0, and we integrate around this way, and we head back to 2 pi. So that branch cut gives us 0 to 2 pi. Negative infinity to 0. And then this gives us negative pi to pi. And this other one gave us 0 to infinity and 0 to 2 pi. Here's some standard branch cuts we can use for like the logarithm integral. The logarithm form. Boom, boom, boom. Just like that. That's pretty cool. So I kind of like branch cuts. They're kind of fun. And all we have to do is just figure out where the log of z, like plug in 0 is equal 0. There you go, that's your branch point. Here again, log of z is equal 0. It's because we don't have any alpha or any a with it. But for the square root functions, we're gonna connect points. Like you can connect if you got like a -1 to 1 or your 2 branch points. Like for example, for this thing, you could plug in a 1, you could plug in a -1 for z, and they'll both give you branch points. So here's your -1, here's your 1, and then you have that situation, you just kind of connect the 2 points. So that's one way you can do that. And, you kind of want to convert this stuff to polar forms. You figure out what the magnitude of z is, figure out what the angle is, and then, you might have to find that angle by going around the unit circle and figuring out exactly, like if z was -1 plus I, then you kind of have to go -1 in the x direction plus 1 in the y direction, and you figure that the angle there is 3 pi over 4. And if you have a standard branch cut, say 0 to infinity, and you're looking for like -1 minus I, that would be in this direction here, you can kind of continue this and you'll figure out that this is 5 pi over 4. And it's still within the 0 to 2 pi bracket. So there are some values that you can find within your branch cut. And there we go. I think that's pretty much what we need to know. Now we also can be worried about poles of functions. So branch points and poles are pretty important. The branch point kind of tells you where the argument is 0, but the pole tells you when you're dividing by 0. So here's a pole, for example, z squared plus 1 is on the bottom. You know that your poles are at plus or minus 1, like z equals plus or minus 1. What's more interesting is when you have imaginary poles. So let's say the function was something like 1 over z plus I, and that's your function, f of z. So you ask yourself, where is the pole? Z plus or minus I. And then the poles are going to be at plus or minus I, right? And so those are your poles. Now, if your pole is at the, like if you take z equals plus I being the pole, then you're in the upper half, like y is positive, right? And if you have negative I, then you're in the lower half, y is negative. So, if you're doing integrals, and you do a little closed contour integral, closed loop integral, there's no pole inside, and you're doing it in the complex plane, complex integral, it has to be complex. It can't just be a regular loop. A regular loop would be different. But if you're in the complex plane, z, imaginary and real, then the closed loop gives you 0. As long as the function is analytic, meaning that there's no singularities, no branch points in or along the loop. So like you can have singularities outside the loop, branch points outside, like intersecting stuff around here, poles outside. As long as inside or along the loop there are no singularities, no branch cuts, no intersecting cuts, and no poles inside, then it's analytic, and therefore the integral is 0. But let's say there's a pole inside the integral. Then that's when it becomes a little bit more interesting. We can use the Cauchy integral. Here we've got our closed loop. We've got like a pole or two inside right there. And we ask ourselves, where's the pole? If the pole's in the upper half, then obviously the closed loop in a lower half will be equal to 0, but the closed loop in the upper half will be equal to this, 2 pi I, some of the residues. If you're in the lower half, then a closed loop in the upper half will be 0, but a closed loop in the lower half will include this pole, so you get possibly 2 pi I sum of the residues. Now, realize that if you're doing this with a Green's function, and you're trying to find like the integral of the Green's function poles are important to look at. But the best situation to do is to take your integral that might be in real space, convert it to a complex integral in f of z, dz, over the real axis. Then realize that e to the iz, for example, would be equal to e to the ix plus iy, which is equal to e to the ix, e to the negative y. And that means that if you're in the that means that in order for this to be not infinite, in order for it to not diverge, then y must be greater than 0. So that way this sort of eventually reaches 0 instead of going to infinity. So since y must be greater than 0, then you have to close in the upper bound. This tells you, this particular analysis here, this complex analysis, tells you whether you need to be closing in the upper or the lower half. Depends on whether you have a e to the positive y or e to the negative y. So if you have e to the positive y, then you must have y is less than 0, so that you must close in the lower bound. This tells you where you must close. Keeping in mind, though, that you might have e to the yt if you're dealing with Green's functions, e to the yt. So now you have to consider both. If it's e to the yt, then either one of these two things must be true. If you either have y is less than 0 or t is less than 0, right? Because otherwise this will diverge. The problem is that since Green's function forces this Heaviside step, then it kind of tells you that for time is less than 0, the solution is already 0. So it's trivial. So time is greater than 0 is really the only thing that matters. And so because of that, it kind of forces y to be less than 0. So let's just say when t is less than 0, in this particular case with the e to the yt, then that means that y must be less than 0. Otherwise, causality and stuff will not really work properly. Alright, so that's a little bit complicated, but here's an example. Let's say we're going from negative infinity to infinity in the real axis, and we want to close in the upper half, because we have a situation like this where we're like e to the ix, e to the negative y. We have to close in the upper bounds because y is greater than 0, and there's no pole. Well, that's great. That equals 0. If there is a pole in there, if there's a pole in the upper half because we have plus I is the pole, then this equals 2 pi I, the sum of the residues. Excellent. Next example is over here. Notice that here we're closing clockwise, so we actually have negative 2 pi I. And if there's no pole inside, then it's equal to 0. If there is a pole in the lower half, then it equals this negative 2 pi I sum of the residues. And we might want to calculate those residues, so here's how we do that. For the simple or the double poles, we have a simple little formula. We take a little limit, maybe a derivative, and then we go. We solve our integral. And that's kind of cool. But as you can see, it's a little bit complicated and difficult. But anyway, we've basically covered the main two topics of this chapter, is that we have these Fouriers, the Green's functions, and these poles and branch cuts and points. All right, pretty fun stuff. Thank you all so much for watching.